We have too many good people to waste time in a group this size. Every minute and a half is an hour of human time. That something just intriguing is that the moon is rising. It is rising in the world. It is rising internationally. It's definitely rising here at home. And I bring it up because these kinds of initiatives have their time, and it's now. And it's always a matter of being prepared, because what flies is what's ready to fly. And together we've cooked up the best game in town, the best game in the world. And people who are really tuned in out there get it. So it is a time in the technical world, a time in the political world, a time in the commercial world to get this done. And the people, so many of the people who matter right here in the room with us today. And I never, ever, ever would have guessed, embarking on this, that we get to the point where the lander and the program to get it to the moon would be handled, and that the rover would be the thing that is a bit of a tough nut and lagging behind. Like, what is that about? And what we embark on here now is a snapshot. It's like a glimpse of where this thing is. With that clear understanding, you know, better get to flight status well under 2 years from now. Anyway, welcome those who have been aboard, welcome anyone new, and particularly the team that made it happen. Let's get going.
So, thanks everyone for coming to the final semester presentation for Cuberover. This is the end of our phase 1 contract. The end of our phase 1 NASA SBIR contract for Astrobotic and for Carnegie Mellon. We'd like the end of the phase 2, when we go to the moon as early as 2020, to look something like that. So what you're seeing there is the concept rendering of essentially the next phase of what we think lunar and planetary robotics is going to look like. Started back on the moon with Lunikad with the Russians, and went on into exploring, further exploring the moon, further exploring Mars. And the next phase, we believe, is the commercialization of and democratization of being able to do science on the moon. So that's what Cuberover is for. Is it's a 2-kilogram rover that should be much more accessible to other universities and scientific bodies that want to be able to do science on the moon. And the Peregrine lander that you saw there is the delivery mechanism for that. This is analogous to the way that CubeSats have democratized access to universities and places like that for doing science in orbit. And the difference between us and others that have come before is primarily that mass, which is what makes it so economical. But what we're demonstrating in this particular phase 1 is that we still can do science, useful science for people on the moon with that 2 kilograms.
I think more fundamentally, there's this really basic question about whether 2-kilogram rover works at all. This is a profound challenge. It's not foregone. We're going to see in an hour whether anybody really believes it.
So the way that we're going to look at that is through a few different phases of the mission that it needs to be able to accomplish in this 2 kilograms to be able to be a 2-kilogram rover. One is that it needs to get to the moon, right? So it has to launch, it has to survive the launch loading, it has to survive the transit to the moon, which in particular gets very cold, and it has to survive that drop deployment that you saw from the bottom of the lander, and it needs to actually rove around the moon. So those those are the phases that you'll hear our different subsystems explain. On a broader level, so there's a variety of different subsystems to this rover that you'll see. At a system level, we have an overarching group that's job is to manage the budgets and the margins between these two groups so that we actually produce a rover that can work on the moon. Those budgets are mass, which you'll see now, power and thermal, which will be discussed, and then the money itself. And we're ensuring staying on that schedule for the launch for the phase 2 and coordinating between these subsystems.
Okay, so to give you an idea of what else the systems teams does, we're in charge of navigating the high-level requirements all the way down to the low-level subsystem requirements. So it's sort of multi-tiered approach. You start off with the objective levels, and that's the goal of the entire Cuberover program. And then the mission levels, basically all sort of rover launch operations. And then you get down to systems, which is, like we said before, the mechanical team, thermal team, avionics, science, systems. And then finally, subsystem teams. To give you an example of what requirements for each of those tiers looks like, we'll look at the example of mobility. So on a sort of objective level, the Cuberover is supposed to provide power, mobility, communications to a sort of science payload. Basically, all that means is that the Cuberover has to be able to do science. And then on mission level, the Cuberover shall be able to move a certain number of distance. And what we have to know is that for the systems teams, this document is a sort of living document. So you can see that the distance that the Cuberover is supposed to travel on a charge for the mission is to be determined. And we will refine that as our objectives or as our components require. And then on a system level, say the mechanical system, we establish that the Cuberover has to have 2 independently driven wheels, no more, no less. And then even more on a subsystem level, we're looking specifically at the mobility subsystem of the mechanical team. The Cuberover has to be able to traverse a certain size of obstacle. So this is how we lay out the entire objective requirements for the Cuberover as a whole. And in addition to establishing a requirements list, the systems team keeps track of a certain amount of allocation requirements. So this is the mass, I think MEL stands for mass or equipment list, and basically what it does is it tracks all of the mass budgets for every component. So again, we break that down by system, and then furthermore, we take the mass allowance that each system has, and then add a growth margin to that. And then by adding all of that, we can account for future growth. So, say if our original estimate is not quite accurate, there's a little bit of margin to grow into that as well. So Manan is next up, here to talk to you guys about the mechanical side.
So for the Cuberover system, we wanted to have a simple yet a robust design. So we did a trade study of if we should have 2 wheels or 4, and as we know that 3 points of contact is the minimal points of contact required to have a stable system, we did some trade studies and ended up going with a 2-wheel tail dragger. For mobility, we have 2 independently powered wheels. So to turn, one wheel would be turned at a different rate compared to the other. For thermal, since the mode of conduction is either, as in heat transfer is either using conduction or radiation, there's no convection on moon, the radiation would happen over the surface that's there. So we wanted to maximize the surface so that we can radiate out heat to the outer space. And for solar power, we will need enough surface area to install solar panels, so that the solar sun would, provide energy, and then we could recharge our batteries. Oleg?
So the primary philosophy behind designing the chassis for the rover is that it must be able to survive and thrive under the thermal environment of the lunar surface. So as the legacy configuration that was developed in earlier semesters, we had originally envisioned a solar panel and a radiator that would be facing on opposite sides of the rover. That way the radiator would be protected from the sunlight that would add heat, but it would be somewhat exposed to a certain amount of heat that comes in from the regolith. And under this condition, we would have optimized our design in such a way as to minimize the surface area of the ceiling. However, if we were able to increase the surface area of the ceiling, that would be the ideal location to place your avionics and to declare it as your radiator. So when we were exploring the ideal configuration that could be possible, then under the idealized rover, we would have a horizontal radiator that would maximize the view factor to open space and minimize the view factor towards the hot regolith on the moon. Solar panels, if any are included, would ideally want to be facing away from the radiator so that they do not re-radiate any of the heat onto the surface of the radiator and heat up the electronics that are bound to the radiator. And also we would like to isolate the thermal enclosure for avionics so that the heat that comes up from the regolith below the rover and any heat that comes up from being collected onto the solar cells is also blocked out. So within this environment, this would have been the original concept for the idealized configuration of the chassis. And this is a schematic that shows that the multi-layer insulation, which essentially blocks out the majority of heat traveling through the floor and being collected by the solar panels, would be protecting the avionics in the upper section, which would be used only as an avionics containment box. Using this configuration, we ran a number of simulations to examine the temperatures that the avionics would produce while bound to this structure, and we were able to find that if we have a certain angle of the sun above the sky, and we have the chips running at maximum power as predicted by the avionics team, then we would have this relationship between the maximum temperature that we see on our chips and the angle of the sun above the horizon. So if our maximum temperature that we wanted to keep the chips underneath was around 40 degrees Celsius, then we would not be able to operate at latitude or at conditions of solar elevation around 45 degrees or higher than that. Using that, we made a prediction of how much the radiator and the maximum chip temperature would be depending on the power that's dumped into the avionics board by the complete set of electronics on the rover and the angle of the sun above the horizon. So this provides a cutoff for different modes of operation on the moon depending on how much power has to be dissipated by the radiator to open space. The initial prototype, however, unfortunately resulted in too much weight, and there were certain issues with its ability to surmount obstacles as well. So when we continued the development past the mid-semester prototype, we went on to a chassis with a reduced mass that was more optimized for the environment of climbing through a very rough terrain. And following this object,
so following the new chassis design, we ran simulations on ANSYS, and this was at ideal lunar conditions at a solar angle of 75 degrees. So you can see the different heat signatures incident on the full body chassis of the rover. And this shows this for the same solar angle but just the chips alone. So as you can see, it ranges from about 29, the hottest it gets is about 34 degrees, and we predicted from the TEL document that the lowest maximum of all the components is about 40 degrees, so we're good in this state. And this basically shows for 3 different powers, so at no power and at half power, which would be at ideal conditions, and at full power, which is the red bar, which would be at when the rover is driving. And this basically shows the maximum chip temperatures for the different solar angles. And as you can see, and the rover is only operable if the temperature of the radiator is between 0 to 40 degrees. So you can see the window there, and at full power the rover can be operated at about 28 degrees till about 85 degrees and still be within range. and at half power, the angle moves to about 35 degrees to 85 degrees.
Quick question.
Yes.
When you're saying degrees, do you mean angle of elevation of the sun, or
Yes,
temperature
sorry,
degrees?
angle of elevation of the sun.
Okay.
Angle of elevation of the sun.
And really quick question, blue, it's idle or zero Cuberover, what are the curve, the legends in here?
Blue is when everything is switched off, which would not happen at all, but we put it, I guess, for the sake of putting it. So this basically shows at different solar angles the maximum chip temperature experienced by the maximum chip temperature experienced. So you can see that at a solar elevation of 85 degrees, at half and full power, we're still within range. So it would still work. Now the limitations that we faced with the current model is that we didn't provide a method for charging like solar panels. So if you do, and since we've not provided a way to charge, obviously if solar panels were included, obviously the heat inside the rover would increase. And the second big limitation is that all the simulations were run assuming that it was perfectly flat lunar terrain, so we haven't accounted for rough terrain. So if the rover is in the vicinity of large boulders, which are relatively hotter than space, then the view factor of the rover towards the boulder would be higher and more heat would be impinging on the rover. So if solar panels are included, the whole plot would shift upwards and the operation window would change. So though you would be able to operate the rover at lower solar angles of elevation, you would lose on using them at higher angles. Yep. Hannah's going to talk about the wheels.
So moving on to some of the component design, as with the majority of this rover, we are comparing and balancing some of the indicators of performance, in this case, maximum surmountable obstacle and later flotation, against weight. So throughout this rover, we are often doing trade-offs between something that we predicted could perform better and something that needed to meet our weight standards. So in terms of the wheels, we wanted to make them for their minimum possible diameter, minimum possible width, as light as possible while still achieving our desired mobility standards. So here you can see some data from a Chinese lunar exploration mission. This mission landed in one of the lunar maria. Maria comes from the Latin word for seas, and these are the planar regions of the moon. Covers about 15% of the moon. They're called maria because early astronomers thought that they were actually seas on the moon because they're a little bit darker. But these are the more flatter, more tame areas that have been the locations for most of the landings on the moon. This is where we hope to land with our rover. So some of the data you can see here, the average height we're looking at, about 0.03 meters. We took that and doubled that. So we're going for a maximum surmountable obstacle of 76 millimeters throughout this process. And this is where we got our radius that we designed for the majority of this project. All right, because we are working on a very non-cohesive soil, the sand on the moon is called regolith, and it's very fine and non-cohesive. So that means that if you were to pack it together, it wouldn't be able to support your weight very well. For this reason, we wanted to add grousers to our wheels. Grousers can help increase the surface area in contact with the soil and can increase the amount of thrust that you can get from this ground. We went with very standard numbers for both our grouser height and grouser spacing that were developed from some of the testing actually at Carnegie Mellon in the sand bed that you'll see in the planetary robotics lab. So we went for 10% as our grouser height, and we made some assumptions to use the equation that you see there to get our spacing. So we made a big assumption for the slip and the sinkage and used this equation to get a baseline information for our grousers. So grousers, we still didn't incorporate anything with different shapes in terms of our mobility testing, like a chevron or a curved shape for the grousers, but this is definitely an area of future research, perhaps in phase 2.
So after we decided we need browsers and the minimum dia, so what we did was a parametric study of how much diameters can we choose from and what could be the width, rim, thickness, and stuff like that. So what you'll see is this is probably the area of interest for us. On the x-axis you'll see the diameter, and on the y-axis you'll see the mass. So we were aiming for 100-gram weight of one wheel. So that's what we were aiming, and that's the green circle you'll see. And then we did another study for the same thing, keeping the diameter around the double of the obstacle height. And then now you'll see how we are varying the width and the rim thickness. And then based on these parametric studies, we decided on a width and a rim thickness. And then as we improved the design, this was our first design with 4 spokes. And you'll see every design being iterated based on these studies, but with different inside spoke design and stuff like that. Yeah, so, and then we did analysis throughout whenever we developed a new wheel design. So what we did was drop test, which is from 1 meter from the lunar rover, and then we checked against if it was safe or not, factor of safety. And then the same thing we did while mobility. If it stalls and the wheel is stuck, what would happen to the wheel? So that's what you see in the middle, max stress, which again is a good FOS. And for vibration, what we did is, so on the launch vehicle, we checked that the envelope of frequencies was up to 100 hertz. So what we took was a factor of safety of 2, and then we did vibe test for them. So what you'll see is the middle is fixed, and then 2 faces of the wheel are fixed. So that's what we would need while it's attached to the rover, is attached to the lunar pod or vehicle or whatever. Kushal will talk about the tail.
Okay, so as we know that we have got a 2-wheel and a tail system over here, so designing the tail was a part of the integral design, and there were parameters based on which we had to select the tail. There were a number of parameters which influence the structure, the shape, and the size of the tail. So our first thing was we wanted to minimize bulldozing effect. As we know, so the tail is the driven part of it. There are no motors connected to the tail, and it is just getting driven because of the wheels in front. So we wanted to minimize the amount of bulldozing that is taking place because of the tail. Thus, there's less amount of resistance which is caused because of the regolith. Apart from that, we wanted to maximize the flotation. So there was, by saying maximize flotation, it means to have higher area of contact with the regolith. Thus, the flotation increases. We also wanted to make the tail easily surmount an obstacle, because there was some of the previous designs where the flotation was good, the bulldozing was good, but surmounting the obstacle, the tail was not doing it that great. And we also wanted to make a tail such that it can work very well in reverse operations. At times, the rover by itself, Cuberover, may have to go in reverse direction, for which we didn't want the tail to sink into the regolith. So, in the 3 images at the bottom are the design iteration process, and now I'll be talking about the final design of the tail and the features of it. So, we start with the load-bearing strut over here at the very end. The maximum amount of load which will be coming onto the tail will be endured by the strut, and since we know like materials are very good for compression, so this is gonna be taking the max amount of load. We've got a contact bulb over here which is designed such that it gives high amount of surface area of contact, thus improving the flotation characteristic of it. It's got a lip at the end which helps in the reversibility part of the effect, and we have tried to make it as lightweight as possible to reduce the bulldozing effect. Apart from that, there is a continuity in the line which is connecting the bulb to the rover. This continuity helps us in going over the obstacles, and there is no change in geometry, or there is no change in the curvature present over there. And we also did some mathematical analysis to find out what should be the angle of connection between the tail and the rover by itself. And we realized that the line which joins the point of contact with the regolith and the axle should be the line along which the tail should be oriented, so that there's minimum amount of force that an obstacle applies onto the tail and it can easily go over that obstacle. We came up with 2 designs, like 2 variations of the same design, a narrow bulb and a wider bulb. And at the bottom we are seeing the video of the reversibility of the tail and just showing that the tail doesn't sink into the regolith. the two variations in the design was to check whether increasing the surface area of contact actually does it help you to significantly improve in flotation and bulldozing, but the experimental tests were not very conclusive, and this is an area which can be taken into study in the further prototypes. As far as the FEA analysis are concerned, we went ahead with choosing 3003 aluminum, considering it to be a better and more optimal choice for space grade aluminum over 6061. We did the initial wipe test to check what is the first natural frequency of the tail. There were a number of possible maximum load conditions, and one of the loading condition was we have got two fixed obstacles on the either side of the tail, and the rover is trying to turn because of the wheels are free to turn, and these obstacles are prohibiting the tail to turn, and we checked whether the tail is strong enough for enduring that type of loading situation. And apart from that, the two major tests that I would like to discuss will be about the drop test. So here we are assuming that the tail is the first point of contact with the regolith, and in the first drop test, the Cuberover is dropping down in a horizontal situation, in a horizontal orientation, but yet the tail is getting in contact with the regolith first, and that has got a high factor of safety. But this one is something which is a bit more it has got a lower factor of safety. The stress developed over here is higher. The situation over here is, since there are multiple points of contact with the lander, we are assuming that by the time that they are deployed, the Cuberover is tilted and it has come to a vertical orientation such that the tail is facing down and the wheels are up, and it is getting deployed in that orientation, and the whole weight is coming onto the tail, and yet the tail is the first point of contact. And considering all these situations, we've designed the tail to endure at least this type of forces which will come onto it. Shreyas will be talking next. Thank you.
So based on everything that they said, we went ahead and got a 3D printed prototype for performing testing. We performed a number of tests on the prototype that you see. It's made of nylon SLS. Some of the tests that we performed on the sandbed itself were for traversal and point turns for the teleop, obstacle surmounting to see if the rover could maneuver terrain, tip over testing, and with the prototype we could change a number of things, like the wheels were detachable, so we could connect different types of wheels, we could connect different types of tails, and thus this allowed us to try out different parameters for our testing. So here you can see on the left is the point turn test that we performed on the sandbed, and from the video you can see that point turn is definitely achievable with this prototype for the teleop. This was a video just showing the maneuvering around obstacles, also on the sandbed. So these tests were performed to show us that maneuvering is possible and also the point turn is possible. Next, Ignacio is going to be taking over.
Okay, so another test that we did was the obstacles for mounting. We started testing with different wood blocks covered with sandpaper, going from around 1 inch to 3 inches, which is 76 mm, and using the 180 mm wheels. As you can see in this video, the prototype is able to surmount these 76 mm obstacles.
Yeah.
And another test that we did for the prototype was a tip-over test. We did some analytical analysis and also like experimental and see how they match. The most critical directions of tipping is the front and diagonal direction. So diagonal means that like the line between the tail and the wheel are in the axis of tipping. And then on the left you can see what is the actual configuration for this prototype, where's the position of the center of mass. For the experimental results we use a small step to avoid the rover to slip, and that maybe can make some variations in the results. So the results were back tip over is pretty safe, 63 degrees analytical, front tip over 36, and it matched with the experimental. And the diagonal one is 35 analytical and is 40 experimental. That maybe that is related with the issue with the step that we have to install for testing. And after that we did like an analytical calculation about what will be the angle of the rover after surmounting the obstacle and then dropping again to the ground. And that angle is 16 degrees, and assuming that we can be in a terrain with a slope around 5 degrees, we get an angle around 21 degrees, which is still safe for any of the tip-over angles.
For the motors, we used two type of motors that were off the shelf: the harmonic drives RF minis and the Polo Loos. As you can see, the harmonic drives used 24 volts. The reduction was 100 to 1. A stall torque only of 0.65 Newton meter, and it weighed 66 grams, which fit well within our mass budget. And we used the Polo Loos, which used 12 volts, with a higher reduction of 172 to 1, with a higher torque as well, which was 1.72, and it weighed on the higher side, which was 107 grams. The reason why we used the two is because we weren't certain as to which one would work well. So for the midterm prototype, we started using the Polo Loos, and we felt that the torque wasn't enough to drive the 2 kilos. And towards the end, we also tried using the harmonic drives, and since they provide lower torque, we were certain that they weren't going to run, but we tried never mind. And then since the torque of the HD minis was low, what we did was create a prototype that weighed 1/6 of 2 kilograms, which is like 333 grams, and we put the two HD motors, 2 wheels and a tail, and we made it drive, and it drove really well. So these were a potential path to flight motors, but we would have to pump up the reduction and get better torque. And as you saw that this rover prototype ran really well, the tail, can you run it again? You can see that the tail doesn't have a big bulldozing effect. It's not sinking while going forward or reversing, and even the wheels, they're hardly sinking. So our rover has a really great chance of working when it comes to lunar gravity, but testing these HD motors on Earth is not feasible with 2 kilograms. So we are speccing different motors that would provide higher torque to test the rover on Earth gravity.
All right, in order to test our mechanical prototypes, we went through a couple different control methods. For the final prototype that you see in front of you, we had 2 different control methods. On the left, you can see a custom motor controller and single board computer setup. This was used so that we could test almost all of our requirements without using the single board computer that's being developed by Avionics. So this that you see on the left has 2 motor controllers that use CAN open, which can communicate with the motors, again, without any of the SBCs that the Avionics team will discuss a little bit later. In addition, this uses an Odroid computer that we could have used to test some of the science aspects, including the camera. So this whole setup was developed to test the mechanical aspects separate from the development of the Avionics team, which you'll hear about a little bit later. On the right is a far more simple version that we use with the Pololu motors that Manon mentioned. This setup simply used an off-the-shelf motor controller that we could use to power 2 motors. In addition, we used an Arduino Mega so we could attach different sensors as we saw fit.
So going back again to the surmounting test, we also did like an analytical analysis of surmounting to check what was the torque required to go over 76 mm obstacle. So this is just like a really basic equilibrium equations for torque, and also to check what is the minimum friction that we need between the wheels and the obstacle. And it doesn't seem pretty good here. But so this plot, what it shows is basically shows you the results for the 2 kilogram rover for two sides of wheels on Earth gravity and on lunar gravity, and here is the size of the obstacle. So for the 76 mm, we are around this line. So these two numbers, 1.6 and 0.33, are important because 0.33 is what we need to surmount an obstacle of 76 mm on the moon, and 1.6 Newton meter is what we need to surmount the same obstacle for the same 2 kilograms rover, but on Earth. And this is what Manuel already mentioned, but since the HD motors are rated for around 0.44 Newton meters, theoretically we can actually achieve this on the moon, but we cannot test those motors with a 2 kilogram rover on Earth. So that's why we're trying to find like some new motors with a higher torque.
So just to bring it all together from a mechanical standpoint, this is where the phase 1 flight CAD stands at the end of this phase. You can see some of the things we've already talked about, which is this new chassis shape for the thermal and the mass reasons, the wheels that we've discussed, the baseline browsers and the radius coming from the obstacle heights, the tail with its struts for loading and for continuity going over obstacles, and then some of the things that we have not discussed yet because they weren't, we know that they are needed, but they haven't been developed in phase 1, they're mostly a phase 2 issue. MLI is used for thermal insulation from getting heat from the regolith. The batteries and the SBC, the avionics team will talk to you about, but you can see they would be mounted directly to the radiator, so they are thermally sunk to the radiator and then can radiate out into space. Those two motors that we've talked about changing the specs on, and then the camera, which science will talk about. You can see that field view on the front. And as we continue into phase 2, we'll further develop this flight CAD and figure out specific integration, specific design for manufacturing, and then testing and final assembly. More broadly than that, there are a few very specific phase 2 tasks that need to be done in mobility. One is to continue to investigate these different wheels. We have made several more wheels than we've tested, particularly WEGs, which are wheel legs, so they kind of are missing rims, which are something that should be examined for testing in phase 2. Wheel refinement, both on performance level and on just a mass optimization level, in terms of changing spoke geometries, potentially looking at compliant spokes with curvatures or dual spokes for stiffness, and then changing browser shapes, which we've discussed a little bit. The baseline is just straight, but there are potentials for chevron shapes or other things that we don't know the impact of that on this mass of a Cuberover. Another phase 2 development is further refining that thermal model and the structural chassis that goes along with it, both understanding design for manufacturing issues and integration with other subsystems, and then how they affect performance and thermal issues. One that you really haven't seen since the video at the beginning is that we do need to drop off of the lander platform onto the ground. That is a major load case for this rover. We need to make sure that we don't tip over. We need to make sure that we don't break. We need to make sure that we can survive launch mounted to that platform and yet release cleanly. There has been some work done into that in terms of understanding that we're in a good tip over envelope for the basic chassis geometry that we have, but actually specifying the operations for that and the specific components is a phase 2 issue as well. And then the last one here, which is most important but happens at the end, is understanding design for manufacturing and actually getting all of those things in-house, getting them assembled, getting them tested, and then sending them on the rocket and sending them to the moon.
Very broadly, the avionics team was responsible for the software, the hardware, and generally all the electronics on the actual rover itself. From the perspective of the avionics team, in our labs, the system that we were working with had the following, like the shown workflow. We had Houston, which we used as a lander interface, and we had the rover, which was controlled by the single board computer. Now this shown is the new single board computer, the RevD that was developed by this in this semester by our team. That will be explained later. And we had a very interactive graphical user interface on Houston, which we could use to give in commands to the rover. We could the semicircular arcs that you see, they show us the temperature readings coming in from the thermistors. On the actual rover itself, they show the temperatures of different parts of the board, different parts of the rover. We can see the accelerometer readings, which would basically tell us the pitch and roll angles, giving us an idea of the orientation of the robot. We can put in a wheel velocity command, and the rover would drive forward at that particular velocity. And even though all that is not clear, the text boxes you see are for inputting commands, basically numbers. One of them is wheel velocity, the others are how much you have to turn the rover by, an angle for a turn, and some amount of distance in meters to move forward. You can input all of that at the press of a button. These commands are sent over to the rover, and the rover responds. So our semester goals were basically on these particular sub-modules. We wanted to do motor characterization to see what kind of torques the motors could support. We wanted to do a lot of, mostly on the programming side and also on the development side of the single board computer, RevC, and then of course developing the new revision of the board, which is RevD. We wanted to test out the sensor payload, which basically encompasses sensors like gyro, accelerometer, thermistors for temperature readings. We also did some work on the radio module, characterizing the radio from the radio's perspective, how far can the rover go outside and still be able to communicate back to the lander, stuff like that. And lastly, we also did work on the battery module to see, the battery module is basically a monitoring system for the entire battery system, how much voltage the batteries have, how much charge is remaining, how do you ideally distribute the charge among the battery cells that we have. We had a dedicated chip on RevC for that. We did some work on that, basically from the software side. Yep. And now Jeremy will take over and tell you about the motor characterization.
So the first task of avionics was to take the harmonic drive motors that we were prescribed by the mechanical team and determine what kind of power draw they would experience at various torques. To that end, we designed a rudimentary system of doing that, which is putting a wheel onto the motor and then attaching this string and varying weights to simulate different torques. The torque data is shown here, and at varying velocities, the power draw experienced at different velocities varies linearly with speed. However, it does not vary linearly with torque. And we found that there are parts of the torque curve where the efficiency increases greatly, and we weren't accessing those until we discovered that idea. So I'd like to get into a bit of what was discussed with the new revision of the board, which is RevD. So what we've changed from the RevC board, which so. This is the RevC board, and this is the RevD board. So first thing you can see, it's a lot smaller. This was done in order to meet the specifications for thermal radiation. We determined that the 15 by 15 centimeter design was optimal for radiating heat, so that the parts were not overheating. This also is a lot lighter. It weighs approximately 100 grams versus 196 on RevC. So about a 50% mass reduction and a 30% size reduction in terms of area. So we accomplished this by removing several extraneous parts. There's on the RevD design, the RevC design, there was a extraneous Hercules microcontroller, which we determined that we would no longer be necessary. And a lot of power things were removed as well. So, but the things that we directly changed was, well, I'll discuss that now, but, so the first thing was this, the gyroscope was altered because it was found to be non-functional. When we tried to test the gyroscope that was on the RevC board, we found that it did not respond. It was not able to be interfaced with SPI, which was an oversight from the previous iteration. This was fixed for the new edition of the board. We also found that one of the charging chips on the board for getting power to the rest of the components from the batteries was not actually the right chip. So we researched and replaced it with a new chip as well.
Okay, so like Jeremy said, we basically focused on primarily streamlining the RevC design, making it fit that 15 by 15 centimeter radiator plate. And one of the biggest challenges was just getting the components to work. There were a lot of pitfalls that were encountered in RevC, and basically the first half of the semester was spent addressing those and fixing those, and problems with the gyroscope, with the radio, Wi-Fi chips. And so once we fixed that and figured out what was wrong or replaced parts, we were able to proceed to designing RevD and carrying through with that. And so that's basically what RevD represents, is a streamlining and a simplification of a lot of the parts and processes that were developed in RevC. And so one of the important ideas of RevD and really of Cuberover in this semester is the idea of customizability. It's more of a platform than it is really just a single mission rover. And it's meant and designed to be able to carry customizable payloads and to vary what missions it's able to go on. So the way that we looked at that from avionics is, even though the reduction in size was pretty drastic, we still found that we have about 20%, about 1/5 of the 15 by 15 centimeter RevD board space that is still available to support putting on other kinds of chips that are specific to mission and specific to sensor payload, which is a really important idea in kind of designing for customizability and for variation.
Okay, so after the design was finalized of RevD, we sent out the design and we got 5 PCBs back. And then we used a reflow process to solder at least one of the boards. One of them is done. And so now I have to test it for correctness and compatibility, make sure there's no shorts. And so, as Jeremy somewhat mentioned earlier, one of the main problems we had this semester was with the gyro. And it measures the angular velocity of the rover, and together with the accelerometer, it can tell the orientation of the rover. And for some reason it had some hardware error that caused it to not be initialized and report zeros back all the time. And so we replaced it with a new gyro, and initial testing has shown that it works, but we need to do more complete testing to make sure it works in all cases.
Another part of the sensor package is the thermistors. And so I guess for those of you who don't know what thermistors are, they're basically variable resistors that change, whose resistance changes as the temperature changes. And the thermistors on the board that we have an NTC, which means negative temperature coefficient. So as the temperature increases, the resistance decreases. And so the purpose is to basically, they're put near critical components on the board. Like for example, there you can see that's the microcontroller, the Hercules that we're using on the RevC, and there's a thermistor right there, which is very small. And so we can just measure the temperature and make sure that nothing is overheating. So the thermistors had a data sheet which provided us a mapping for every 5 degrees for resistance to temperature. And we plotted this curve, so basically how it works is the microcontroller reads an ADC value, so an analog uses the ADC converter to read a value for resistance, and then we use this curve to actually convert it to a temperature and get useful information out of it. We also did a characterization of the, it's not really visible. Okay, so I guess this isn't really very visible, the curve, but it's like a light blue line. Does not exist. Okay, I guess I don't know why why the curve isn't visible, but from the characterization we can see that.
You want to draw it? Just a shape?
Sure. So we have measured. Yeah. So we have measured temperature. Actual or expected temperature. So that's what the curve looks like. It's kind of squiggly at the bottom. Ideally, it should be a straight line that, which has a one-to-one correspondence, because that is what you would expect. But at low temperatures, we don't see ideal behavior because the Rev C had issues where there were leaky resistances that were very small that ended up being in parallel with the resistors. And so at lower temperatures, we would expect a much higher resistance than we see because these small resistors would bring down the resistance significantly since they were in parallel. And so ideally they should be fixed on the Rev D because all the wiring was changed. Finally, another thing we had to work on was the battery module. So initially this was placed in the Rev C because we weren't really sure whether we'd use solar charging or not, but now that we know we aren't, it's basically used to, the main purpose of this module is to do cell balancing to ensure that all the cells in the battery are at similar voltages. So the whole process involved was, initially on the Rev C, there wasn't the right chip on there. Like, it was just fit the footprint, but it wasn't actually a charging chip. So we had to reorder a new charging chip, put it on the Rev C and test it. And then when we tested it, it didn't actually work because the Rev C had faults with this, in the wiring from the power to the charging chip. So we created a new board with this new charging chip and then tested it by hooking up an Arduino to this charging chip. So the Arduino supplies 5 volts, we used 3.5 volts to 3.3 and then plugged that into the charging chip. And we were actually able to read voltages from all the cells that were connected so that we could measure them and see if one of the cells was too low, we could do cell balancing to ensure that all the cells were the same. The issue with cell balancing was that we tried to do writes to the charging chip, and that didn't work even though the Arduino never gave an error, and we saw a signal was going from the Arduino to the charging chip using an oscilloscope. And so I guess a future thing to fix would be figure out why the why that signal when sent to the charging chip never actually was received.
Could you go back to that just because it's flying by? So,
yeah.
The cell voltages are not balanced; they're not even. Number 5 is 3.97. Number 1 is 3.06. That's not close to being balanced.
Yeah, exactly. So, basically, how the charging chip works is you write a bit to a register and say, I want to enable charging in this cell or cell balancing in this cell.
I see.
And so that's why we needed the writes, but the writes aren't really working.
I get it clear.
Yeah.
Okay.
And so now we'll talk about the radio.
So the radio module was one of the important parts on the SBC itself. It allows communication back to the lander. The module we have is called WF121 from Blue Giga. It's basically a Wi-Fi module supporting communication on the 2.4 gigahertz channel. It supports a bunch of different protocols like 802.11bgn. We're using N if I remember correctly. And it also has a big 32-bit microcontroller to control its functioning. So the thing about this radio module is that it has to be programmed using an altogether different programming language, scripting language called BG script, which is similar to BASIC in its layout. It gives us like an event-driven platform, so you can have a few lines of code, blocks of code that execute only when a particular event happens. You have a packet coming in from the UART, from the microcontroller, you need to send it out. So you'll get a notification, you'll have an event triggered when that packet is coming in, and then you can program the module to send it out through the Wi-Fi interface. And you can do the same thing when a packet is coming into the radio and you want to relay it back to the microcontroller. You can program it for that to respond to that particular event of like a packet coming in. So we needed to understand how far the rover would be able to go away from the lander and still be functioning, still be able to communicate. We started with an initial round of radio characterization using this development board. This was developed here by one of the students from the previous iterations of this class. We started out by using this, and to our surprise, we found significant packet loss at around 91 meters, which was very much less than what we were expecting. We later found out that we were using the chip antenna for this radio module was not the one we had on the actual SBC. We were using just the chip antenna, which is much less powerful. It has much less gain, so the range is also constrained. And we actually chose the spot near the painted fence for this, which also had a lot of obstacles, and multipath propagation was probably affecting our range. So we moved on to another round of testing on the football field. So we put the entire SBC REF-C module on a skateboard, and then placed Houston at one corner of the football field, and then moved the SBC outwards. We initiated packet communication and then started moving it outwards so that we could measure when the packets started dropping off. So yeah, the REF-C, basically done with the REF-C. And the thing about this was that we could attach a very small dipole antenna to the radio module so that it would give us better range. This is what we plan to actually use on the actual rover itself. Yeah, so you can see Houston placed in a corner over there, and I included that picture to give you an idea of the range that we went to. We went even beyond the corner of the football field in about approximately 6 meter steps, 6 meter long steps, and we were measuring the signal strength of the radio at each point. So I guess the graph is a little clearer on this. You can see how the signal strength dropped off with the distance. We could see that it flattens out at about 160 meters away from the lander, from Houston, and the range turned out to be much better. We observed like 206.5 meters for complete packet loss, but this figure is also not perfect. Is not a perfect figure because at larger distances we had huge obstacles. I mean, we actually went out all the way to the road to Margaret Morrison Street, so that's a huge distance away from the lander. So we can definitely, from the radio's perspective, the rover can definitely be communicating back to this distance, up to this distance, away from the lander. So now Philip will talk about the finite state machine implementation.
Yeah. Well, if you develop software in the beginning, you always have some experimental software, and you just have a loop, and you run all this code throughout the loop. But if you're coming to operation, you want to have a finite state machine. So you want to separate your codes into different steps and use them. So if someone is a bit familiar with the astrobotic payload, we have a pre-launch phase, we have a launch phase, we have cruise, and we're in the lunar orbit. So these are like all different states. And in these states, we are only allowed to like sometimes communicate to our rover and not always. But basically in all these states, we want to monitor the important components of our board. We want to control the heat for our battery because we have to ensure that the battery is always heated at the right temperature. Yeah, so monitoring is a really important thing we will use throughout the whole process. We divided it into two different kinds of monitoring we want to use. We have a simplified and extended monitoring. The simplified monitoring will basically execute it in every loop. We want to do it like constantly. There are like the battery is one thing we always want to check, accelerometer data, and especially the thermistor, because we need the temperatures of the board. We want to have like some extended monitoring for parts which are like not that important to survive, which we just do like in a specific time frame, like where we say we do this extended monitoring and check all the components of the board. We will have settings. So even if the rover is already out in space, we still maybe want to adjust thresholds or other things during the mission. So we will have a state where we can set different settings. This is especially also for the science, because then we want to maybe adjust what we're doing with our science. When the rover is actually on the moon and it's going to do a surface operation, first thing is like we have to boot all the components on the board. We have to initialize the microcontrollers, start monitoring, initialize our communication, and initialize the motor controllers, check if the rover is fully functional. Then we want to shut off the motor controllers because we want to have the wheels turning freely. And then we want to drop. Then we're going to test again are like the motors working, microcontroller, everything works. We'll do a short mobility test, and then we're gonna start with our science. And the science mission, basically, we're monitoring it, we are taking photos, we're sitting, and we're driving. In order to sit and to drive, we need some opcodes. So one is sitting, we just sit, we shut down power components we don't need actually at the board. When we're driving, we're setting a distance and an angle to the rover in order to move. And science, we want to say, take pictures, maybe in a different resolution, to perform our science we want to do on the move. So future work, it's not done with just making a board. A board is something good you can see, and it's a great achievement for the semester, but there are a lot of components we have to further test. So first thing is we have the MSP430, which is basically a chip which controls the board, which can shut on different components. We have to program the code. We're currently working on that to switch on the different board components and switch on the Hercules in order to get the board running. As you've seen, the gyro code already worked. We just have to implement this new gyro code for this board. Then it's all set up. For the battery module, we have to figure out how to do battery balancing. This is like a really important thing which has to be done pretty soon. We also have an RS422. This is basically just a connector, which is simulating a connector to the lander, where we have the opportunity to send signals from the lander to the rover. And this was, for example, like if there's an input signal coming, then please shut the whole board on. We also have the solar module still on the board. If in case we want to do something with solar power in the next semester, the option is there, it has to be tested. And we also have the FPGA in order to, we have to develop code for it and like see what we can do for our science mission with this component of the board. And then of course, power testing and Carnot testing is like, what components do we need, what's happening if we shut off several components, what is like the power draw still. We want to verify what's going on in this board. Now I want to hand over to science.
Thank you. So the mission of the science team this semester has been to answer the second most important question of the project, which is not only can we build the rover, but can the rover gather scientific data that is meaningful? To determine this, we've used as a guide NASA's posted strategic knowledge gaps, which are, in essence, questions that NASA wants to answer in order to improve its current designs and improve its future missions. And we need to keep in mind our current constraints. So we are building a 2-kilogram rover, and it has to use an apparatus that is hopefully under 100 grams of mass and under 0.9 watts of power. We also want to keep in mind that it has to be effective on the moon, and that if we choose an apparatus other than a camera, then we're adding mass where we could perhaps answer scientific questions with only a camera. So these are some of the strategic knowledge gaps that are feasible for a Cuberover. We could study the distribution of hydrogen species and other volatiles in the moon. We could study lunar dust remediation, essentially technologies that would allow the rover to function and mitigate the damage caused by regolith, surface features of regolith, electric and plasma environment, as well as surface trafficability and blast ejecta phenomena. We did trace studies on different devices that we could use to study all these questions, and on most cases we found that they were either too large or too massive for our constraints. So we decided instead to maintain our current setup, which is only to have a camera, and yet have enough space that we could accommodate some kind of payload if we wanted to answer other questions in the future. Our goals, therefore, are to focus on the last two SKGs, which are trafficability and ejecta phenomena. We want to know whether near the lander there is patterns or different levels of regolith that we can study, and we also want to know further away from the lander whether we have issues with trafficability and how often we find obstacles that we cannot surmount, questions like that. So today we will discuss all the different types of testing we conducted.
So we conducted tests outdoors just to measure the quality of our camera. We conducted tests on the CNC, which allowed us to change height and change angle. We conducted tests on the sand bed to see features on soil that would match regolith, and we also did a comparison with a SolidWorks ground truth model. Our drivers are accuracy and feasibility. So we want to know whether it is possible for a camera of this type to detect differences in soil constitution and in general soil features, and we also want to know how accurate we can have our images be. This is the camera we decided to use. It has space heritage and a good resolution in addition to mass and power that are under our constraints. In fact, it's under our mass budget by nearly 75 grams. In terms of software, we decided to use SolidWorks to create our computer model of scenery that we were studying. So in the CNC testing, we created a SolidWorks model of every obstacle that we had. And we used eCamView to take pictures in Visual SFM to put those pictures together and create a point cloud, and then MeshLab to compare the point cloud to the CAD model.
Okay, so the first testing we did is the outdoor testing. So the purpose of doing this testing is trying to prove the capability of our camera, algorithm, and the software to do the reconstruction. We pick up this thing specifically because there are many rocks on the pathway that have an average diameter 4 centimeter. So we want to see if we can reconstruct these rocks. The picture on the left is a picture from our camera. And the picture on the right showing the reconstruction model that we construct from the camera. As you can clearly see that some feature from the image, such as the rocks and the wall on the right side of the pathway, can be well reconstruct. And the reconstruct validate our algorithm that our camera can reconstruct the rock as small as 4 centimeter in diameter, that from the perspectives achievable from the Cuberover. So once we have this preliminary result, we move forward to the next thing. The next testing we did is the CNC testing. Here's the testing setup. As you can see, the light gray box on the right of the CNC bed is objective. It's a target that objective we want to reconstruct here. We attach the camera to a spindle of the CNC machine. What we did here is to move the CNC bed toward the object, taking the picture and trying to reconstruct the model from this picture. So here is the image showing the actual setup for the CNC testing. You can see the target object that we want to reconstruct is the parallels. So we set up the parallel on the right of the bed in a specific layout that we know the dimension and we know the dimension of the parallels. We attached the camera to the fixture that we made has the 0 degree and attach that fixture to the CNC machine. I want to move the CNC bed toward the parallel to take the picture. So the way that we collect the image data is we have 4 parallels, and we will vary the height, vary the angle, and we want to move the CNC bed along the 25 centimeters pathway to take a picture every 0.25 centimeter. So we know that in total we have 101 image for each iteration. We designed the height between 2.5 and 7.5 to meet the requirement of the design, mechanical design. And we also want to pick up the 15 degree because we know the field of view for our lens is 68 degree. We want to use our camera to do both navigation and reconstruction. If we want to have a better reconstruction while we still do the navigation, we want to our field of view is about 20 degree above the horizon. That's the angle that we think that works best for our application. So in order to quantify our result, in order to quantify our reconstruction model, we created a ground truth model in the SolidWorks. So basically what we do here is to use the point cloud from the reconstruction model to compare the point cloud from the ground truth model in the SolidWorks. So here's the testing result from the CNC machine. So as you can see, we have 3 reconstruction model. From the result, we visually tell that all the testing at 0 degree does not have the valid result because we barely to see the view of the shape of the parallels. So we decided that we want to use 15 degree. And from the view, we can tell that the 7.5 centimeter is the best model that we can get from this testing. But we still wanted to have the quantitative result to verify our result here. So what we did here is to match a point cloud from the CNC testing to the point cloud of the ground truth model to see how close our each reconstruction model to our ground truth model. So the algorithm we use to calculate this closeness between 2 models is Hausdorff distance. So we're taking the mean of the Hausdorff distance of each data point from between the ground truth model to the other data point of the reconstruction model. So the lowest mean Hausdorff distance we calculate here is 0.0131 millimeter for 7.5 centimeter above ground reconstruction version. So we know that this result, this quantitative result, match our view result from the previous slides. So once we have the best optimal angle and the height determined here, we move forward to the next testing we did is setback testing. So the purpose of doing this is want to see if our camera can do a reconstruction in a better representative of lunar surface. So we put some feature in the setback here. As you can see the picture on the left, the rocks mimic the obstacle that we might have on the lunar surface. The gauge block is the object that we know the dimension, so we can use it as a reference. And the parallel in the middle is a parallel that has 0.86 millimeter, which is thinner than the top layer of the regulations. We want to see if we can pick it up. So the result on the right of the picture shows that our camera can pick up the parallel that's even thinner than the top layer of the regulations. And this result helped us to prove that our camera do have the capability of doing a science test. So now let's talk about the future work and conclusion of our work.
Right, so just as with every other subsystem, there's more that we can do in phase 2. So for the camera reconstructions, we can improve them and expand on the testing that we did by adding some more height and angle tests, testing various exposure time and brightness, which is something that we had played around a little bit with, but not too extensively. And we can also test the quantity of images that we need in order to create a very good reconstruction. In addition, we are planning to investigate and test other science instruments, some of the things that Fernando had mentioned earlier. So for now, though, our recommendation that we gave to the mechanical team was that the camera should be placed about 4 inches, which is around like 7.5 centimeters above the ground, and then it. What?
10. Your conversions are all wrong. Are your inches right or are your centimeters right?
Inches should be right.
So 10.
My apologies. That should say 3 in. That should.
Your other slides are wrong too. So.
Right. Well, my apologies for that one. Okay. No, the 4 inches is correct. Sorry about that.
Okay.
And the angle is at 15 degrees. Yeah. Yeah. No. You're right. It should be. It should all. The 2.5 should all be 5. 7.5. Yeah. Should all be 10. Okay. My apologies for that. And then I believe Systems now has something that they wanted to say.
So yeah, the semester is kind of like over, but we had during the semester a lot of like stumbling blocks we had to face. The biggest one, I think, from all our perspective was the motor and the driver. Normally for a moon mission, it should be the thermal that you can that your rover doesn't get fried. But we had a lot of problems picking the right motor and having the right driver controller in order to drive and test it. The second thing was like, it was a big decision to make, like that we don't charge this rover, that we are not using solar panels. That also helped us to go further in our development and make a final decision. If you have too many variables, it's like really hard to come up with a prototype and a solution that actually works. The next thing was like we found out a lot of like information by actually testing and moving this rover around. Simulations are good, but like if you really test something, you have it in your hand and you see how it performs, it's way better than just like running a simulation and say it will work. That's a total difference. And also, yeah, the SPC board, I think everyone knows the story who was in this class, this board. The component selection was kind of like difficult, and getting it out, it's finally manufactured. We're all glad for that. In the next phase, there's a lot of awesome testing everyone can be excited about. We already heard about the deployment test when we're going to drop the rover for the first time. We also have a lot of flight qualification testing. We're going to use, as shown in the picture here in the mid, like a shake table in order to shake the rover and see how it's performing in vibrations, and also like a thermal vacuum chamber in order to simulate what's going on if there's heat around. It's not done so far. And of course, we have like some concept of operation. We want to see, can this really work? Can we, it's the software and also like the mechanical parts all working together. And we want to see this rover moving forward. So finally, I hope you all believe in it, and we give you like a good impression why this rover should be feasible and what are the challenges to make it feasible. At the end, I have to say there was like a lot achieved this semester throughout in science, in avionics, and mechanical, looking at some regolith, designing the wheels, making a tail, making this whole assembly, making a final board. Like thermistors are also important, and also having a thermal design. So we want to say thank you for that, and I think that's a great achievement we got for making this rover possible. But I think there are people who supported us the most, and we have to thank Astrobotic for their help, like coming to us and answering our questions and having that experience to help us. Of course, we have to thank Red for giving us a lot of advice on how to design a rover, and yeah, Carnegie Mellon, of course, as well. And this last picture is for everyone who kind of like helped us, but it's not a person maybe in this class, maybe somewhere here around campus. We don't know him that well, but there were a lot of people who supported this class in order to make it possible. And yeah, I mean, the rest is for the audience probably. And the final thing, Red always told us, buy, make, code, and decide stuff. So this was a team. That's it.
Great. Okay. All right. Questions? Anyone?
That's it for the science team.
Yep. Also, just heads up, we have like 4 minutes.
Oh yeah, this is
oh my!
You should check out Reality Capture on Steam. It's a lot better than SFM or BSF.
Will do.
Very
Nice.
easy. It's like $40 a month.
Sherman?
For the avionics team, I was wondering if you guys considered radiation hardened components at all.
Yeah, so we've been looking right now into just getting a fully functional board that drives the motor, or drives the robot and just works. We've been talking about things like, for example, right now we're using a Cyclone from Altera that we're probably going to switch for Linux, FPGAs, or Xilinx, because they're usually performing better in radiation. That's something that is for future work, either phase 2 or beyond.
Lou is in the back, and since there might be just a minute or two, he can go back through the history of selecting components for which there are hardened counterparts, with the exception of maybe a handful.
Yeah, everything that we've chosen really is either has a space equivalent or has been tested in radiation, like the Hercules microprocessor has had some radiation testing done at NASA. And there's also
It's actually a pretty low rad mission. It is quick to the moon. It is a fairly short surface duration, and if all were known, at Carnegie Mellon, we've tested plenty, and there is plenty of heritage behind it. Maybe some other question. Anybody?
Looking at the image on the bottom left, it seems like you could shrink the body a bit. Is that something
Yeah.
you've considered for weight?
So
or?
we're kind of leaving that in the margin. There is this pushback, it's a commercialization thing, so there is supposed to be some kind of payload bay for the science instruments. It's not well defined, so we're trading that with.
You showed lots of wheels. I don't know if you can go back to some of them, but your designs had things like 3 spokes and 16 grousers. I won't go through all of them, but then you get around to prototyping, and it's 5 spokes and 12. From the look of things here, is there any rationale? I mean, the adage in all technology is never reinvent the wheel. And what you can count on by any robotics program anywhere is that it will constantly invent wheels. And this one just looks like it hasn't quite gotten there.
Yeah, it really hasn't converged yet.
I mean, some of them are just like these wide rims and unknown numbers of grousers and unknown spokes, and maybe not a good idea of how even the mechanics of that fit together.
Yeah.
Somebody else?
What material are these wheels? In your sim, in your analysis, what material? What material are those?
1661.
Yeah, I'd just say something about materials. There was lots of mention about here's what's in the future. And if all were known, there's not much optimality of material in this. It's not quite designed or built like a watch. And even Carnegie Mellon, that pushes a lot of buggies around, uses carbon fiber. And there just are likely to be more optimal structural prospects for this. Somebody else?
I actually think that's all the time we have for right now. There are people waiting outside.
Well, just to, here's the thing. It doesn't get better, and that last voice that spoke up is quite a leader. We were so, and are so fortunate to have Andrew and to have all of us and to be up to something that's worth being up to. Let's clear the room to be good citizens. Thank you for the year. Thank you for the outcome.